I'm Matt Godbolt.
And I'm Ben Rady.
And this is Two's Complement, a programming podcast. Hey Ben.
Hey Matt.
How you doing?
Very good.
Excellent. Well, we don't normally refer to things that have happened in the news because that gives us a certain flexibility in the order that we release these recordings.
Right.
But you and I were literally just talking about the fact that Broadcom has bought VMware, and we were going to talk about some level of containers versus not containers versus virtualization versus whatever, and it seems like we should bring that up. So
yeah,
let's talk.
Seems like a good topic.
Right, exactly. It's such a deep one, and you know we've got varying levels of experience in different technologies for essentially what is, how do I make sure my software works in the environment that I'm expecting it to? And I'm thinking personally from this point of view, like a developer who deploys server type applications, headless applications that run on machines in the cloud or in data centers and whatever like that. But I guess actually now I'm saying that, I was sort of giving that so that, you know, I can't say too much about how UI stuff is developed. But then there's a number of software packages I see for Linux these days that come as a pack file or a what are those things called? There's a bunch of different snapshots, which are essentially here's a whole operating system's worth of application wrapped into a file system and then presented as if it's like a single thing. And it's like a Docker container, right? But differently. So it's everywhere. And I think we all want software that's easy to deploy and run, but there's a number of ways of achieving it.
Yeah.
What are your thoughts?
Well, I mean, I think it's interesting that I think you and I have a sort of a similar perspective in that we look at those tools that way. And if we asked somebody who, you know, was a little bit more focused on infrastructure, they would probably tell us something similar, but definitely not the same in terms of like being able to take, you know, a fixed amount of hardware that they have provisioned and paid for and, you know, have pre-purchased the electricity for and have backup batteries for and have networking for, and say, okay, well, how do I take this sort of fixed resource and allocate it out to all of the needy, greedy software engineers who keep telling me that they want more servers? Oh, I got to have a server for this app, and I have a server for this app, and a server for this app. And so, you know, I think from their perspective, they might see some of these virtualization tools as a way to you know, manage those resources more effectively and have a little bit more control over not only just the resources themselves in terms of memory and compute, but also the sort of blast radius if one of them, you know, goes horribly wrong, right? Like, you know, being able to, you know, wipe an image and give someone a fresh new server with a few clicks of a button is way easier than driving down to the data center and unracking a machine that is no longer responsive because somebody did something terrible to it. So
I don't know what you're talking about.
Yeah, I've never done that.
Never done that. Oops, I just fork bombed my own machine. So you're right, actually, that's a very valid point. Those infrastructural things are super important, and it's sort of a funny thing. I was talking about it at lunch with a bunch of folks the other day, and regaling with a story from my past and a friend of mine who used to work at a big airline, and those folks are still using mainframes, and mainframes have always been able to do all the things that we're now kind of starting to rediscover in that virtualization world.
Right.
You know, like, hey, you want more
Yes.
CPUs? Yeah, we can bolt more CPUs on while the mainframe's still running. Hey, you want to shut down the mainframe, do maintenance, and bring it back up again? Sure. What we can do is we can teleport the mainframe's image up to a backup site. Nobody even notices that your connection is now going to Manchester instead of London. And your terminals keep on responding. Everyone's still doing their requests, and the batch jobs are still going. Meanwhile, they power down the main machine, fix the RAM, and then you can teleport it back. And those things have been around for, you know, half a century. And yet we're rediscovering them in terms of what, I mean, specifically you're mentioning things like VMware allow you to manage the resources really fine-grained and make those kinds of like, hey, we need to move from one machine to another machine. It's sort of miraculous that it works as well as it does.
Yes. Yeah, because those mainframes were clearly designed with those specific use cases in mind, right?
Hardware capabilities to do those things.
Right, right. They built those things from the ground up with like, okay, we're going to be able to do this offsite backup and we're going to make sure that it all works. And with all these other things, we sort of backed our way into it because it's like, clearly there's a need to do that. But, the old school operating systems and CPU architectures and all these other things that we have, maybe someone gave that a thought a long time ago, but they certainly didn't design the whole ecosystem from the ground up to be able to do that.
Right.
And so now we're sort of in this state where it's like that need is still there, the desire is still there, and it's this sort of tricky problem of, okay, well, how do you actually do that?
And yeah, folks like VMware have got their solution for it. There are obviously other vendors that can do it, and of course, I mean, one should note as well that the chip manufacturers have been slowly heading this way too, adding more and more like hardware level virtualization things. Because like we've always been able to do these things. It's like my hobby of writing little emulators for old machines. Once you can fully emulate something, of course, its state is just a bunch of numbers that you've got. You can move that around anywhere you like, and then kind of carry on somewhere else, and have your single step through each frame of a game, and then go backwards because you can just emulate from a snapshot, one fewer frame forward, and keep that kind of stuff. So this has always been possible, but it was just infeasible to do it without actually running the same CPU as you're trying to virtualize and the same hardware. But then things have come along. But I feel like we're going off base from where I was thinking of going. I just got excited, which is what this podcast is about, right?
Yeah, yeah. No, I mean, I think these things are all kind of related. You can, and maybe I don't think we should necessarily dive into this at the start, but one place that you could maybe take this is like, this isn't just about virtual computers, it's also about virtual networking equipment, right? Like if you look at, some of the tools that are out there, it's like, yeah, you think that this IP address is a switch, but it's not. Like
I mean, one only imagines what's going on in like the AWSs and the Google Cloud infrastructure in terms of their physical network separation and their ability to, as you say, make it look like you have your own cloud to yourself, knowing that actually no, those fibers are the same fibers that everyone else is using between all of the racks. It's all magic.
Right. Yeah. But yeah, talking specifically about the part of this that is, I as a software developer, somebody who's sort of building a total application, you want to be able to deploy it. That's really important. You want to be able to connect to the machine that's running it and troubleshoot it and read the logs and run TCP dump and netstat and all the other wonderful tools that we talked about in some prior podcast. And still have the flexibility of the things that we were talking about in terms of making maximal use of those resources and being able to tear it up and down and being able to build the definition of what that system is in a configuration file rather than in a PC
Here's
part
a checklist
picker.
that Barry has to go down and make sure they all look the same, right?
Right. And so there's lots of different tools to do this, but I think they all sort of serve the same need. So what are some of the tools that you've actually used in anger to do this?
Well, I mean, the main one that springs to mind, other than bespoke ones that I guess became Kubernetes. When I was at Google, there were some things that became sort of like strange containery type things. I don't know if it's exactly the same thing now. I think it out loud, but the one I have the most experience with is Docker, and Docker is a great solution to I want to have a reproducible environment that's incrementally built with layers, and so it's relatively efficient if you are only changing the end layers. And you can definitely have that kind of feeling of like, well, if I have a Docker image that I can give to you and you're going to run it, then I am 99.69% positive that if it worked on my machine, it worked on your machine, because what I in fact did was ship my machine to you, and now you're running my machine, which is a blessing and a curse. And I think that's the problem, right, is that it can be misused, like anything, like any technology. My experiences with Docker, so Compiler Explorer started out, actually it didn't start out with anything, it just started out with a shell script running the Node.js on a bare machine, and then very quickly it was like, how am I going to manage this? So I decided to use Docker rather sensibly at the time, and Docker served us well for many, many years. Docker did not scale with the gigabytes and gigabytes, hundreds of gigabytes of compilers that I wanted to build into the image. The images took longer and longer every time to build. We're going to take a pause there while my wife comes in through
the couch.
Through the back, through the couch.
The couch I never realized that there's a door behind your couch.
How else do you get between places? We put flue powder in, and then we can go anywhere to any other couch.
Diagon Alley. That's how this works.
That is exactly how this works.
Sorry.
It's okay.
The back
door's jammed. Okay, the back door's...
Oh, no. So you had to come in through the couch door.
They had to come in through the couch door. All right, there goes my dog. And then we're going to have to try and remember what I was saying and work something out. Or just pretend it didn't happen and just put this in and, give our listener... I was just thinking, actually, I hope our listener isn't called Barry, because I always use Barry as my general dog's body person.
Oh, yeah.
To do
I think
Barry.
I say Steve for some reason. I don't know why that name.
That's
Steve, yeah.
So we were talking about Docker.
Yeah, you're talking about using Docker in Compiler Explorer.
That's right. So the problem with bigger and bigger images is that no matter how you cut it, you're uploading layers upon layers upon layers upon layers of a piece of software with more and more compilers, and it was just getting unwieldy. And there are definitely tricks you can do with volumes and other things like that. And we looked at them for a while, but ultimately we backed it out when we realized we needed more security than Docker would give us. There were at the time there were some relatively high privilege exploits for breaking out of Docker containers into the wider world, and we were kind of tacitly relying on Docker to also be a sort of protection domain. And the other thing is that if you're running inside that container, even if you don't get privilege escalation outside that container is long lived. So if you're like servicing somebody's request and it was a poison request and it was able to monkey with the system, it's now monkeyed with that running Docker container. And so it's going to be there until we restart the machine or restart the Docker container. So there were some things we didn't want, properties we didn't that we wanted to get in terms of jailing. And once you're in one container, you can't have a container inside a container and inside a container arbitrarily, or at least at the time you couldn't. So we switched out to a different approach where we just have tarballs and run them on the operating system. But it did serve a need for a long time. And it's a frequent question we get asked is, hey, do you publish a Docker container of a Compiler Explorer instance that I can just get started, because people do just want to do Docker run, blah, blah. And you get that benefit. It just works. Yeah, we have different ways of achieving that, I think. But so anyway, that's my experience with Docker. I also have used it at a number of places at work, and I think it works great if you plan very carefully your Docker image layout and the layers are sensible and well managed. And
yeah, so when you say a Docker layer, what do you mean? What's a layer?
So Docker logically is a file system, a whole operating file system. It has it literally untars, for want of a better explanation, into a bunch of temporary directories and then overlays each directory, one directory over the other. So you start with a base image, which is maybe like your entire Ubuntu distribution, and then you're like, oh, the first thing I'm going to do is I'm going to install these 20 apt packages that I need, and so the next layer will be another file system that only contains the things that change between the base system and the system where you ran sudo apt install my 100 packages I needed, my extra packages. And then the next layer might be, oh, and now I'm going to copy some files from my Git repo that I'm running it in into the container at a particular location. And that's another layer of the file system that only contains those copied files. And then so on and so forth. Each layer would add in more bits of the software and configuration. And the cool thing is, of course, is that you only need to regenerate layers that changed, and of course the layers that are immediately after them. So if I change, for example, the base Ubuntu image, of course everything depends upon that. So I'll have to rerun the commands that populated the later layers and create new layers. But if I'm just changing my application software and I don't change my dependencies and my system dependencies, then oftentimes it's only that last layer of a few 100 kilobytes or so that changes. And so not only is the build time faster, but the way that Docker distributes itself is as compressed layers. And very often, of course, if you're upgrading software time and time again, those base layers are already on the system in the cache somewhere. And the only thing that you need to do is upload the few 100K each time, which is fabulous. Yeah. So that's a really good way of having a sort of incremental deployment of your software.
Yeah. So what happens if I have like a layer that's like fetch the latest version of this thing from the internet?
Well, that is an excellent question. And that is one of the biggest problems with something like Docker, is that it's very easy. Docker caches based on the text contents of the command it's going to run.
Oh,
So if
okay.
you just say curl get me latest version of something, pipe through tar ZXF or whatever to extract it, then that command will run exactly once on your machine when it populates that layer. And then if you run again, having changed the contents on the website that you're curling from, or like a new version of the software is released, and the URL doesn't encode that in some way, you're getting,
Right.
like
You're getting latest or whatever.
bob.latest, exactly right.
Yeah,
Then you won't see that. But unfortunately, anyone who later builds with your Docker container will see that change. And so these things will not necessarily agree.
Right.
And so it's really important that if you are fetching external resources, and it's so easy not to get this right, but if you are fetching external resources, that you get like a specifically named version of everything that you want to get, for two reasons. One, it means that you get reproducibility if someone else grabs your Docker file and just says, build me this, please. And the second thing is that necessarily, if you want to change that image, you have to edit the URL that encodes the git char or the version number or whatever, and which means that it will be rebuilt automatically. But it's hard to do that right, and it's hard to make sure you apply that everywhere.
Right.
Even things like the base image itself, oftentimes when you say in the Docker file, hey, I'd like to build something based on Ubuntu 2004, that's essentially what you say. You say from Ubuntu :2004, from Ubuntu latest or something like that. And those are kind of like a git pull of whatever someone has tagged as being the 2004 for Ubuntu. If you really want to make sure you get reproducible builds, you need to put the char hash of that particular layer in the get command as well, so that you're always going to start with the same version. And of course, there's a duality there, right? It's convenient from my mindset. It's great to have a totally reproducible build. Mm-hmm. And that means that I can hand you a Docker file, not the contents of the Docker image, right? That's different. But if I hand you just the text that says, this is how to build my world, you will get the same answer that I got every time. And that's really powerful. But it's super inconvenient because every time some little trivial fix in the base image is pushed, a security patch or a security fix or whatever, then I have to think to go back and change the char to be the latest one. And that kind of feel, if I want to keep those things going. And of course, the first thing you're going to do, this is almost always what the first line after the from Ubuntu is, not sudo because you're running as root, is apt-get update and upgrade and update, right? Because you want to pull in all of the things that are latest. And there's no kind of version for that. There's no bitemporality to that. So you're a bit stuck at that point. And that factors into where some of the problems that one has with something like Docker. It's a boon, but you have to be really careful how to use it and have to understand these slightly sharp edges. And maybe most people don't care about those, but I know that it's affected us before, and we have you and I have definitely got an industry where we really want to be able to reproduce what we did before and understand it. It's also very easy to generate gigantic layers. If you think about if you don't design your Docker file correctly, So in the example I just gave, apt update, apt upgrade, apt install, right? Those are like sensible commands I might type myself if I had a fresh new computer that you handed me.
Right.
The simple thing to do would be to run them as 3 separate layers. And that makes a lot of sense, but I've pulled down a whole bunch of stuff and replaced a bunch of there's a load of temporary files that get pulled into the apt directory that I probably don't need in my production image. I've then updated a whole bunch of stuff, which has replaced a bunch of stuff. And then I'm like maybe installing my own packages. And maybe I remove some system packages that I don't want, right? Mm-hmm. And so I've got 3 or 4 layers, each of which is strictly additive. And then there are sometimes if you had to delete files, so you might be tempted at the end of that to go, and the last thing I do is rm-rf var apt cache, right? Kill the cache. I don't want it anymore. It's like gigabytes of all the intermediate crap that was downloaded while I was installing my packages. But if you put it as a separate step, unfortunately, those already exist. Those intermediate files exist in a layer. That delete can't remove them from the layer. It just marks them as being, you can't see them anymore. It puts tombstones in there. And so your overall size, the number of bytes you need to ship around, still contains the layer that has all of those files in it, and then a separate layer that says, and by the way, all those files are gone now.
Right.
So you have to be really careful. So what people end up doing is writing a long stanza of like apt-get and update and as like one giant long single bash command. And at the very end of that, rm-rf var apt cache and depackage -- purge caches, all the things as one thing. So atomically, all those things happen, and then it's just the end result that gets shipped as the layer.
Yeah. And that I've definitely seen that in Docker files, and it's sort of this like, it just reads as gobbledygook as at the start of the file, and you sort of parse it and you sort of figure out what's going on there, but it's not the sort of like clean, one instruction at a time, maybe with a helpful comment as to why you're doing it.
And
that
you see sometimes people will write shell scripts that they then copy into the image to run and then delete again afterwards, just because then the shell script is essentially atomic from the point of view of the layers. And it could be a tooling thing, it could be just what you'll get used to. I don't know, but it's easy to get wrong.
Yeah.
And the thing is that as a developer running locally, you tend not to notice these mistakes because it's necessarily incremental. You've been doing this, you've been building on and building on and building on.
Right,
and then when you ship when you Docker push for the first time, you discover that you've got several layers of gigabytes each. And I'm sure you've done this as well when you've pulled someone else's Docker image and you're like, oh my golly, what on earth is it pulling down?
Why is this Docker image so big as a game that many have played and few have won? It's a really painful experience sometimes. You start cracking open the layers and trying to figure out what the heck is going on, and it's just like, oh geez, why are we doing this?
Right.
Yeah.
And I think a lot of the time, people reach for Docker because it's super convenient, everyone understands it, and it does solve a very real need. But I think oftentimes, in my experience with the kind of things that we do, at least, a tarball of the code that you're going to run, maybe containing the node.js binary you want to run it with, or maybe because we're in a luxurious position where we own our machines. They live in a data center. We know which machines they're running on, which are probably virtual machines as it happens. So that's another layer of virtuality above all of this. But if we know a lot of things about what version of libc is it running, what base operating system are we running, what things can I assume are there, which of course is now a dangerous game to play, which Docker kind of makes you address fully. But most of the time you're like, well, okay, if I've got libc this version, I'll just pass along all my dependencies, right? And it's not that big. For native applications, often a bit of a few environment variables, and suddenly now all of your DLLs will be looked for inside the directory you ship, and then you just like copy them all with you. And that's a bit bigger, but we're talking tens of megabytes of library files here in a little tarball that you extract and will run on a developer's machine and a remote machine. And I guess the other sort of critical part about Docker is that it requires elevated privileges, which means that there's a lot of monkeying around with which user you're running as. And that sometimes is useful. Sometimes you want a totally unprivileged user that's isolated from the rest of the system. And in the kind of, was it 12-factor type model where an application sort of consumes, only logs to standard out, only reads and writes to external things through TCP, that's fine. You treat it as like a black box. But very often it's tempting for developers to kind of go, well, it'd be really convenient if I could get to this set of files on the network, or if I could write to this log directory. And so you start passing things, you start puncturing the isolation that Docker gives you. And then suddenly you wonder why on earth you've got 100 files that are owned by the wrong user. Excuse me, there's a truck going past. But you run this command and then you like try to delete it afterwards, and it goes, "I'm sorry, I can't delete that. You need to be root." And you're like, "Wait a second, I'm not. How are you root?"
Yes, how did you write this as root? And I think it is really an unfortunate thing that the default behavior of Docker is to run as root, because it's really easy to sort of fall into a trap of building an application that accidentally, for really no good reason, needs those elevated privileges, right? Like if you had just been forced to think about it for a minute, you would have been like, oh, well, we don't. I mean, the dumbest example I can think of is like we're binding to port 100 instead of 2000, right? Like there's no reason in the world why that integer matters to anyone, but if you build a whole application, it's like, yeah, there's 30 other apps that connect to port 100 because that's the port that we chose. And not realizing that requires elevated privileges, then you've just added a whole bunch of, you've added a constraint completely by accident.
Right.
And running as a non-privileged user, you'll find that out right away, right?
Right.
And there are other things like that too. And I feel like it's almost like the testing thing, right? Not on brand.
Oh my gosh, testing, you say?
Yeah,
Tell me more.
I haven't talked about testing in like a podcast and a half. So
I know. All right,
you've got part of the reason you write the test first is to make sure that the resulting solution that you come up with is testable, right? If you build something and you don't think about tests and then you try to add the test later, it's really hard. And so most people don't, right? And the reason for that is, well, you came up with a perfectly reasonable solution if you completely ignore this other constraint. Yeah. And then you try to add it in later, right? And so you're doing kind of the same thing when you run apps in as root in Docker. Is you've got a constraint that would be nice, but you don't even think about it until it's
invisible. Which okay, so I'm going to take the other side of that, just to sort of in the defense of a Docker style thing. I know obviously this is there's many a nuance here, but one of the things that Docker gives you kind of out of the gate is deployability, which is another thing that if you don't think about right at the beginning, it's hard to retrofit. We've all seen applications that you're like, well, this is all well and good if I can git clone and I've got full access to the internet and then I can run these commands and I've got access to these things and I can do whatever. And you're like, that's great on my developer machine. Again, the loudest truck in the world is now outside my house.
They're circling. They're just circling.
They really, no, it's just, he's taunting me. He's reversing it up. This has been the most. I will try and edit some of these things, but I think if you can hear this, dear listener, then I failed to edit the podcast very well. All right, I think they've gone. So, but yeah, where were we? I was ranting about something.
You were about
as
to
is
defend
my way.
Docker.
I was defending. No, the deployability is an important thing to not have to retrofit afterwards, and Docker kind of hands you that straight away. You're like, well, Docker pull, Docker run, amazing, right? My CI is Docker build and Docker push, and my runtime is Docker pull and Docker run. And the cool thing is that my developers can run as if they have the CI build because they can Docker pull as well and then Docker run as well. And so it ticks tons of boxes, right?
Yeah.
It's so lovely, right, from that point of view. Yeah. Again, until you discover that half of your computer is now owned by root and you don't actually have root privileges on it. And then you're like, well, I'm stuck with these files, I guess.
Yes, right. Until you fire up the container and then RM them from the container
inside
because the container has root.
I mean, a good friend of mine, I will not drop them but a good friend of mine has a one-liner that gives you actual root privileges on the machine that you're on if you have Docker available with non-sudo. It's a convenient little thing to remember and just click it. Oh, that's so.
Right.
If you have Docker, you basically have root.
Yes,
even if you weren't allowed it in the first place.
If you work in one of those horrible environments where they don't let you have sudo on your own machines, which is insane, but they do exist, you can maybe put in a request for Docker instead and get basically the same thing.
Let me just say that this is a personal opinion that Ben and I hold. Don't want to get anyone in trouble with their security teams. Please don't do anything daft with that information. But it is true, and it's great for taunting your infrastructural and SecOps folks if you indeed need Docker for whatever. Anyway, that's Docker. Other container solutions. I mean, containment as well.
Solutions, like from the Ghostbusters.
Like from I was actually thinking the same thing. Yeah, the light is green, the trap is clean.
So I mean VMware. So we kicked off this whole discussion with VMware and virtual machines, which are a very different kind of technology than Docker. Do you think you could give us a 2-minute overview of the differences between something like VMware or VirtualBox or other sort of virtual machines and Docker, having built many virtual machines in your life?
Well, my virtual machines have all been 8-bit, which makes them considerably easier on some axes. But so let's explain a little bit about how Docker is working. So at least Docker on Linux, which is my only experience here. So Linux supports namespacing. That is the ability to make groups and resource allocations that are kind of contained and have their own namespace away from anyone else running on the system. And now obviously you can think about a user is a sort of a namespace of vaguely, but if you type PS as a particular user or PS AUX, you can see all of the other users that are running on the system. In this instance, namespaces can contain off areas of the operating system so that like the main operating system can see what's going on. But if you're inside that namespace, if a process is inside that namespace, it only sees things in its own namespace. And namespaces can be file systems, they can be users, they can be CPUs, and that may be C groups, but there's a number of things, like aspects of the system which can be compartmentalized and held separate. But you're still running the same operating system and you're still doing all the things that you were doing before. You're just making a new namespace. So what Docker effectively is doing is making a new namespace, creating inside that namespace a bunch of links to the outside world for things like the terminal, for things like network is another namespace you can create, and you can make a namespace. You can make a bridge then that talks one namespace to another, as if it was one of those network devices that we're talking about. And then you're basically running like a regular process, except that if you type PS or if you type LS, you'll only see the world that the container gave you through giving you your own namespace. Mm-hmm. And it's a bit like if someone's ever looked at like chroot jails, which was like the precursor to this, where you could say, hey, start a new process and pretend that the root directory, like the /, the top of the hierarchy, is this subfolder I just made. And then you can never see outside of there. And you can imagine that you're effectively in a jail. You can't see outside of there. And your process can run along and be isolated. And you can see how you might build like a duplicate operating system image in there and then run it. But it's running really on the main operating system. And that has a really interesting side effect. The kernel calls that you're making are going straight to the host operating system's kernel. There is no kernel that you're running inside your Docker container. So if you're running on kernel version 5 point star, and there's some whiz-bang new feature that's in kernel version 6 and above, and you've got a Docker image that's Ubuntu 24, whatever, that wants to use that, it ain't going to work. No amount of Docker magic will make new features appear in your running kernel. Mm-hmm. Virtualization, on the other hand, takes this down to the hardware level and pretending effectively like oh God, now the distractions are a cat hitting the microphone. At the virtualization level, you are pretending that you have a CPU and resources, network resources and hardware resources that don't actually exist. And then a full-on kernel boots up in that world. And as far as that kernel is concerned, with a few caveats, it thinks that it's running on a real computer, but it's actually running on a simulation of a computer that's running on the real computer. Now, it's
kind of like how we're all living in a simulation.
We are all living in a simulation, which explains an awful lot.
Yes, right.
But yeah, we're all living in some kind of the matrix, and all we're doing is we're putting another matrix in our matrix so that we can run another copy inside of that. So as far as that virtual machine is concerned, it is a full sovereign computer in its own right, and it can do anything it likes, unaware that when it says, hey, I've got a network device over here, what's really happening is that some kind of trap is happening in the CPU when it's accessing or trying to access that device, and an operating system one layer up in the list of matrices right. goes, oh, wait a second. And much like when a regular operating system misses a page and has to swap it in from disk, and like the process is put to sleep, and while the image is read, and then it kind of goes, oh, the memory is there now. The same thing happens at one layer above in what's called the hypervisor, which is like the operating system running the show for all of the operating systems underneath it. And so that hypervisor can arbitrate access to the real network cards and the real physical block devices, like the hard disks that are in the machine that you're emulating. And then when you say emulation, you think it's going to be super slow. And in fact, you could obviously write a genuine emulator, and then you could pretend to be an ARM machine when you're running on an x86 or whatever. What typically happens is that these are hardware accelerated. The CPU knows, quotes, that there are layers and rungs of the hierarchy of simulation environments, and it gives the hypervisor more privileges than the operating system underneath. And in fact, mostly nowadays, the guest operating systems, as they're called, are in cahoots with the virtualization layer. They actually do know that they are living in a simulation, and that allows certain things to be a lot faster. So instead of actually having to emulate a real network card, and like as with this sort of two-way back and forth between the hypervisor and the underlying operating system, there can be some kind of agreed thing of like, hey, I'd like to talk to the network card. I'm just going to put all the data I would like you to look at over here, and then, hey, hypervisor, imagine that a network, you did whatever the network card thing did. There's a certain amount of collaboration. I'm making that up in full disclosure. But what that means is that when you go to your Amazon account and say, I'd like a new computer, please, that computer is not a real computer. It is just a virtual computer running on someone else's infrastructure. And you get a certain number of CPUs, and a certain number of disk IOs per second and all that good stuff. And this then comes back to the VMware thing that you were saying at the beginning. This is why infrastructure folks love it, because I can buy two 128 core terabyte RAM machines, and then I can hand them out to as many developers as I like in like 2 or 3 or 4 CPU slices, which I can't even buy. I can't buy a T2 CPU computer anymore. Yep. And they get to share it, and they all have root on their machine, and there's no way they can bust out of their virtualization environment to get to the hypervisor. But they can like blue screen, their kernel can panic, the whole thing can go down. It's exactly like a normal computer, except that really it's just 1/10 of the physical machine you're running on.
Right. So when the annoying developer tells you that they need a server to run their app, and you ask what the app is, and they're like, well, it's this Node.js app that runs in one thread. You're like, there's no way on the planet I'm giving you a $10,000 server to run a single-threaded Node.js app. So I'm just going to give you this one little slice.
And you think it's a server, and it has its own operating system, which means obviously there is your storage requirements, both in terms of memory and in terms of disk space, go up, because like there is a real honest to god Linux kernel running there, and probably on the sibling CPU, like literally on the die 2 millimeters away from you, is another CPU running someone else's Linux kernel, and never the twain shall talk to each other.
Rowhammer issues and other things aside,
don't give me an in to talk about that kind of stuff. Actually, all right, we're gonna have to now, because you poked my buttons. So
Rowhammer, though.
Not Rowhammer, but that's definitely one for another conversation. But what a reasonable person might do, given what I just said, is say, well, the hypervisor is sat there not doing very much, doesn't need any CPU resources most of the time, because it's reactive to the host operating systems that are really running on the CPUs, right? But we could potentially say, well, let's give one or so CPU to the hypervisor itself, and it can do some background maintenance activities. What if it scanned through all of the physical memory of the computer and went, wait a second, I've seen this 4K page before, right? I've got every single of my 60 guest operating systems have all loaded up variants of the same Linux operating system. Why the hell would I have the same 4K pages, like many, many, many 4K pages that are exactly the same, because they all loaded like, VM Linux 4529, whatever. Why don't I just point them all at the same actual physical location and then discard the copies of it, but like pretend to all of the individual guest operating systems that they have their own copy, and then it's just copy on write. If they try to write to it, then they get their own copy. A bit like, when you fork a process on a single operating system, the same tricks happen. Makes perfect sense. Now, obviously, you have to do it retroactively. When you fork, you know that every page that you currently have is going to be shared in the child process, but this is a sort of emergent property of once you've booted a machine up, eventually some pages will be the same on one machine as they are on another, in which case you deduplicate them, and then you're right, you've got more free memory for the system as a whole. And it seems like there could be nothing wrong with that until the security people come along.
Yes.
and they say,
ruin everyone.
Exactly. So it was shown that, and maybe I won't go into too much details for two reasons. One, I don't necessarily know the details, and two, we've probably talked too much about this already. It was shown that if you have the same implementation of OpenSSL or one of the other cryptographic libraries as a co-located virtual machine to you, so I'm going to just go to Amazon and I'm going to ask for 100 EC2 instances, and then I'm going to run a test to see if I can find that I'm co-located with my target. Just by coincidence, I happen to be running on a machine that also has an SSL process somewhere in it, all right? The chances are that obviously those 4K pages will be deduplicated because it's the same .so that we've both got. It's OpenSSL, Ubuntu, whatever version, right? Now I can start doing timing attacks because I know my physical RAM is associated with the same physical RAM that they have. And so if I know which code paths are taken in their code, I can poke around in my cache and sort of try and determine whether or not...
the keys, basically?
Exactly.
Like, I got this byte of the key, and I got that byte of the key, and I don't have it all yet, but that's close enough.
It took a long while to read this bit out because it must have been an L3. But if it wasn't, then I know it must be in someone's L2 somewhere. And that someone might be, and all these kinds of things. And you can imagine how terrifying that is from a point of view of security. You've lost the isolation between the virtual machines that aren't even meant to know that their siblings exist. So that's your own fault, Ben.
Worth it.
We can talk about Rowhammer another time.
Worth it.
So in terms of deployment, though, I mean, you sort of alluded to that by saying that, like, as a developer, it's convenient to be able to go to your infrastructure folks and say, can I just have a server to run my little Node.js app?
Or not even talk to them and just like run a script that generates one for you, and they keep tabs on it and they know who's allocated to, and they can call you up and say, hey, you're using 35 servers. Do you really need them? But,
that's
you can
very
automate
true.
Those things, right? And it's really great when you do.
That's very true. I mean, I forget, of course, that this is what Terraform and what the like do for me in Amazon, right? I just say how when another computer appears. It's never occurred to me that really somewhere behind the scenes all this magic is going on to make that happen. But, it just does. Right. And, that puts a lot of power and responsibility, but a lot of power into the developer's hand. You don't have to, like, overload a machine. And you get the isolation that, say, a Docker container would give you, but at a much deeper level. Now, different problems, again.
Right.
At least in your own server, if it's running as root, well, it's only running as root because you made it run as root. Right. As root. Right? You got every choice you like.
Yeah.
So what do we think about that in terms of like the trade-offs? What would make you choose one method over another?
I mean, I tend to lean more toward, having virtual machines and having more of like I'm going to get this virtual machine. I will probably build some very lightweight automation to set it up. But again, the setup of it is mostly just, kind of like you were saying, the app update, app upgrade, maybe install 1 or 2 system packages, but hopefully not if I can avoid it. And then just run all my applications as a user, as an unprivileged user. And, every version is a new tarball that gets copied up to the computer, or maybe have some automated thing that pulls them down from a central repository.
You've got like a deployment thing that you use, haven't you? You've got like, is it Git deploy?
Oh, Git deploy?
Is that open? That is open source, right?
That is open source, yeah. So Git deploy is sort of my Heroku style deployment script that I made that will let you take any server that you have SSH access to and basically push to it as if it was a Git repository, and as a side effect of that, if the push works, that is, your code is not out of sync with everyone else that's deployed to it, it will deploy your application and start up. And so you get to sort of use the Git semantics around push and pull as your mechanism to make sure that you don't accidentally clobber someone else's deployment.
I see.
Right. And it's sort of a safer way to be able to empower people to deploy locally from their machines, if that makes sense to do. Now, sometimes that doesn't make sense
always make sense, right? Yeah. But...
in fact, it sort of usually doesn't make sense, but sometimes it makes a ton of sense, and it's really nice to be able to do that in a way that is safer than just, SCP, right?
Right, but I mean, often, there are also places where, or times when you want to be able to push to like a development machine, a development cluster, and that seems like a good thing there, where I would actually want, the feature is I have a code on my machine that I want to have running in an environment that I can't reproduce myself locally.
Right.
It's not ideal to be in a situation where you can't quite reproduce it locally, but sometimes, I want to batter it with 200 machines that are going to send queries to it, and so I want to deploy my version that has my fix in or whatever.
Yep. And I mean, you can take, speaking of virtualization, like you can take these things a lot further. And one of the things that I've been playing around with one of my projects is sort of getting rid of the idea of the production environment. So all of the environments in this project that I'm working on are just branches. There's the main environment for the main branch, and that's where the DNS entry for the top level domain points to. But if you make a new branch, it will automatically spin up a new environment, and it will marshal all the services that environment needs, and it will do everything that it does. And so if you want to make a change that involves potentially making changes to the infrastructure, like, I'm going to change a security group, or I'm going to change, the number of servers from 4 to 5, or whatever it might be.
Yeah.
You just create a new branch, you push that branch to GitHub, and the infrastructure magically appears. And the name of that infrastructure is literally the name of the branch. So they're tied together in that way. And when you delete the branch, the infrastructure gets torn down.
That's super cool.
The main branch is always there. That's sort of the quote-unquote production environment. But if you were to ever delete the main branch, it would also actually tear down the production environment,
which
is like
what you want, though.
It's sort of a weird thing, but it's like
no,
just coupling those two things together very tightly and saying a branch is an environment. There's no such thing as the dev or the test or the UAT or the production. They're just names of branches.
Right.
And that is only possible because of virtualization. You couldn't do that any other way.
On a real machine. For all the reasons. I mean, cost was what I was about to bring up, because, that I'm sort of trying to move Compiler Explorer towards a system which is a tiny bit more like that, where instead of the staging environment that we do tests in being kind of like just a subcategory under the production environment, it's like its own AWS account, effectively. And then I can do the kind of things that you're talking about, like, hey, let's have a new load balancer. Let's try out a different way of doing everything in the staging environment. But for me, that's prohibitively expensive, because those resources are not free, and they're quite expensive. Like, having one load balancer is expensive enough. And I can configure that one load balancer to kind of say, well, if it has /staging in the thing, then goes to this subsection, right? And that's how it works at the moment. But so there's a trade-off to be had there. And obviously, in a world of infinite resources, it's no problem that if you create 12 different branches, you've got 12 environments. Right.
Well, one of my subtle motivations for doing this, and again, I'm trying this on my own project, but maybe one day I'll get to do this in a more widely shared company environment, is to directly manifest to the bean counters the cost of so many different branches.
That's amazing.
It's sort of like, branches have a cost, and it's hard for you to measure that cost because it's mostly cognitive load on developers. What if we just turn that into dollars?
Actual dollars.
And then you could measure them and be like, then you have accountants yelling, why do we have so many branches?
As one of those folks that sends out the emails and the nags to people saying, like, hey, this PL's been open for 3 years. Is there any chance of it being closed? I totally am down with that.
Right.
Yeah, the cognitive load. When I hit autocomplete in the for my branch name, I'm like, what the heck is this? This person left the company 2 years ago. Why is it still here?
Right. Yeah. Why is this here?
Those kinds of things.
Yeah.
No, cool. I like that approach. I like the idea of manifesting, and I think obviously you've talked about doing it in terms of virtualization. Mm-hmm. There are ways and means of doing it with the Docker style approach as well, and I know we're kind of getting close on the amount of time that we've got available, but I'd like to sort of suggest, there's the Kubernetes type approach. There's Nomad, which is a HashiCorp system which can be used to run Docker containers, and then there are definitely load balancer type things that can talk to those containers, and you could definitely have it so that every branch that you commit builds a Docker image and pushes it to a named tag for that branch, and then auto registers a container, a job running in Nomad to say, hey, I'm your project - your branch name environment that has all of these machines running. So it can be done too. You are still paying the cost. There are processes running in one operating system or one set of operating systems that is the Nomad cluster or the Kubernetes cluster or whatever. It's a sort of lower I guess it's higher level. I don't know how you describe it, where it's cutting. Is it lower level or higher level than virtualization? Actually. It's definitely higher level, like measured on the axis that makes sense to me right now. But so you can achieve it using that too, which is great. And I mean, I think all of this kind of comes down to is what we're talking about at this instance is infrastructure as code, however it's achieved, be it VMs or Nomad machines running Docker stuff. And so we've kind of strayed from the original point about like what how does one do deployment, how does one use virtualization, what different things are available. But
they're all related though.
They are, I guess, related. Yeah. And that infrastructure as code thing is super important to be able to say like, it's not, no one has to rack a machine. Right. No one has to physically move any cables around when I
Yes.
stand up this instance here. And that instance is defined by a piece of code or a configuration file that's generated by code, or just a configuration file that a human edits, which, you know, is a fabulous way of tracking. I mean, we're especially as software engineers, we know where we stand with source control and CI and things like that. So having the physical world work that way too, and be able to roll back and all that kind of stuff is super cool. However, so it's achieved.
Yeah.
All right. Yeah. Well, this has been a fun exposition of what on earth can we remember about how all this stuff fits together?
Yeah, I feel like we only really touched on it. Like you could probably do a whole other hour on these topics. Like, you know, talk about Kubernetes.
Absolutely, yeah. I mean, I don't know enough about Kubernetes. I mean, I used Borg at Google, which I believe to be related in some way, but I don't know either. I remember them trying to pretend that it wasn't called that, and they used to pretend that it was Anita Borg. It was named after not clearly the evil people in Star Trek.
Right.
Which, yeah. And I think that was because it leaked out because they weren't laundering their referrers. And so people were running internal services from machines, and then people would link to, I don't know, YouTube, not YouTube videos, because that would be Google too, but, you know, link to other people's websites. And then someone went through and what is this? All the machines had names DNS names that uniquely refer to the job that was running on it, which is super convenient for everything. You know, you want to hit your job and it's running a web server, then you just go to that long name and it hits the machine, and the machine then looks at the name you gave it, and then it redirects it to the correct port for that particular instance that you were running on. And then there you are. There's your job running, and you can look at it. But obviously, if you then have a web page on there that has hey, click the cat animation, you click the cat animation, then you've leaked, you know, 12.7.borg.google.dns or whatever.
Right.
Oops.
Refer headers, man.
Yeah. All right, we should stop talking. We should stop talking. We've got plenty of things to audit, to edit, that included.
And audit. We can't let the Borg stuff leak out.
That's true. That ship has sailed.
Cool.
All right, I'll see you next time.
Bye.
You've been listening to Two's Complement, a programming podcast by Ben Rady and Matt Godbolt. Find the show transcript and notes at twoscomplement.org. Contact us on Twitter at 2CP, that's at TWOSCP. Theme music by Inverse Phase, inversephase.com.